Next up, we have Dr. Iskander.
So good morning. So today I will present our product ID-Substrate. Today it's part of AMS PDK. It's about systematic prediction and prevention of substrate noise coupling effects. It was patented since 2015. So the presentation outline, I give a hint about Intento design story, the European project AUTOMICS. We will see together the ID-Substrate at a glance, and then practical case studies, and then what Intento offers. So actually, I started in 2008 as an associate professor at University Pierre and Marie Curie, and then I started to do some research work. I got a European grant for a European project on electrical cars. It was 2012. And then I worked also on the automated design of analog. So I started to put some patents on 2012 too. In 2015, we made the first fundraise from public and private investors, and I hired 7 employees. In 2017, we made another round of fundraise, and we became 16 employees in the company. Among them, we are 10 PhDs. Starting from 2018 and beyond, we are starting to commercialize the technology worldwide, and then start our first step for scale-up. So Intento design, it's about informed decision-making for analog. This means that for each step in analog design, we ensure for the designer that this step is correct by construction. So Intento is focusing on creating a cognitive software to ensure first-time right analog design. So our mission is to create a software that analog designer would love to use. So today I will present ID-Substrate. We have another product called ID-Explore, and we have another set of design services called ID Services. So I would like first to give a hint on the AUTOMICS project that I coordinated between 2012 and 2016. It was a European net grant of 3.55 million euros, and all the main actors of the European automotive industry were present in this project. I would like to thank them for their scientific contribution. And the objective of the project was to create a CAD framework fully based on open access standards that would allow to systematically detect and prevent all kinds of substrate noise coupling effects. And this was mainly intended to protect smart power ICs from all kinds of coupling between the digital part that represents the intelligence of the chip and the analog part that represents the force of the chip. So if we look at an edge bridge, we have P1 and N1, this is the first branch on the left, and P2 and N2, the second branch on the right. And the load is just a motor. So the edge bridge allows to control the direction of rotation of a motor. So if we look at during the operation, we can have the out1 above supply conditions. It means that it's greater than VDD. So the Q1 parasitic appears as a vertical parasitic. But we can have also another condition on out2 that goes below ground. And here we have another kind of Q2 parasitics, a bipolar. It's a lateral bipolar, where we inject the current in out2 in the NWELL, and we collect it from different other NWELLs on the right side. And this parasitics is very difficult today to model because it depends on the geometry and the technology itself and on the doping profile of each point in the substrate. So the traditional AMS design flow today cannot model the propagation of minority carrier injection in the substrate because there are some limitations that exist in the SPICE simulator today. And most of the failure caused during circuit measurement and fabrication are due to the substrate effects. So it forces us to do some circuitry design and refabrication, which increases the cost of the fabrication of the chip. So on the right here, we see the traditional IC design flow, but this design flow cannot really work for small power ICs. So the objective is to propose a methodology or a brick that we need to add into this flow to do systematic prediction and prevention of substrate coupling effects due to minority carriers, and to build a CAD framework on top of this. So when we developed ID-Substrate, we had three main components. We had open access standard, this is the main database. We had OAX POP library, it was the Polygon Operators that we used to do all kinds of meshing. And we have the OS script Python that we use to do the testing environment. This is the architecture of ID-Substrate. So we start with the layout, which is the green square or rectangle. And then we do three phases. The first one is we reduce the layout. We get rid of all kinds of layers that we don't need. And then we do the meshing of the substrate. And then we extract the netlist in 3D. This netlist extracted is function of some parasitic model. We call it enhanced model. So when we create the substrate netlist function of these parasitics, we can generate also the pin connections to the schematic, and then we have the final netlist, which is the parasitics connected to the substrate network connected to the circuit netlist. So this is the key concept of how it works. We have the layout in 2D. We get the Z direction, which is the depth of each of the layers in the Z direction. We divide the chip into cuboids. Each two cuboids, we generate one parasitic in one direction. And then at the end, we have a 3D equivalent substrate netlist. So let's see in how it works in the real layout view. First, we have, this is an NWELL inside the P-Substrate, and on the right we have the layout view. So what we do is that we take this well on the left, we divide it into layers in a vertical way in the Z direction, based on some rules, and then we mesh each of these layers. So the top layer, we mesh it on the first rectangle on the right, the middle, the second rectangle, and the bottom, the third rectangle. So this is what we call horizontal meshing. And we see that each of these squares, 1, 2, 3, and so on, is just a cuboid with the height and width and length. Each two cuboid, the type of material between each two cuboid determines the type of the parasitics. So if we have a P-type connected to an N-type, it's a diode. If we have a P-type connected to another P-type but with the same doping, it's a resistor. If we have an N-type connected with the N+ type, for example, it's a homojunction. So if we see now the whole process, after we divide on the right the N1 into 3 layers in the Z direction, we can generate the top, middle, and bottom. These are the meshing in the horizontal direction. And then on the right, we generate the connection between the top layer and the metal contacts, and then the top and the middle in a vertical way, and then the middle and the bottom in a vertical way. So the meshing on the left are the ones that are horizontal, and on the right are the meshing, the vertical ones between each two layers, starting from the contact metal. So for example, if we see the NWELL, which is the yellow part, the DN tab, the NWELL actually is formed 4 diodes on the edges, on the top layer, and then on the middle layer. But also on the bottom layer, between the DN tab and the P-Substrate, there is another well. So it will be at the middle bottom layer, we will see a vertical diode. So this is how we model the well actually. It's a diode around the well, and then a diode at the bottom of the well. So we did all kinds of meshing of the open access shapes. So each of these forms, we can mesh it in a particular way, thanks to the library OAX, the Polygon Operators. So this is a true example that we simulated. We have 2 diodes representing 2 NWELLs. So the first step is the P-cell view. We flatten the P-cell view we get step 2. And then from step 2, we reduce the layer, we remove the contact layer, the metal layer, and so on. We get the reduced view in step 3. And then in step 4, we get the meshing of the two wells. So here is a zone view of the two wells. We see that we have 4 diodes around each well. Okay. What we would like to do is to study the effect of the distance between the two wells on the current, propagating from one well to the next well. So here is also the vertical layer, the last vertical layer, which has a diode at each bottom of each well. So we made of this a case study where we would like to see the effect of the distance between the two wells on the current. So when we inject the current in one N well and we collect it from the other well, what will happen is the distance changes. So we started the first test with the 20 micrometer N well separation, and the second test we did it with 60 micrometer N well separation. So here we will simulate a single N well. We will inject current in the VN and we will collect from the VP. So it's like a diode. And we see here that the diodes are matching exactly the electrical behavior of a single diode in different temperatures. But what is really interesting is that if we simulate this structure with the TCAD simulation, we see that it will take 341,000 mesh elements. But if we did it with ID-Substrate, it will take only 178 elements. And the difference in time is huge, between 1200 seconds and around 5 seconds. So this means that if we can do a spectral simulation, like the network of the substrate, it will be much faster than doing TCAD. Now let's study the effect of temperature of distance. So we have 2 trials here. One with 20 micrometer, and then we separated with 60 micrometer. We see here that we have almost the same current distribution between the TCAD and the SPICE simulation. And also we have a good agreement with the alpha parameter, which is the gain of the bipolar in each case. If we check also again, we see that the TCAD will be 325,000 finite elements against only 510 elements. So this also confirms that we can simulate by SPICE instead of doing TCAD simulation. So we went also further that on the layout view, we can draw on different layers the distribution of minority characters, the density of minority character distribution. So here, this is top layer. We have the current injected in these points, like the green one. And if we go into the next lateral layer, we see that the current distribution goes around the first rectangle and then propagates away. And if we go again down, we can see that the current really is not propagated in the green area. We used also the OS script in Python to do all the regression tests of ID-Substrate. So here we import open access, and then we import the Polygon Operators, and then we import our extraction tool, the ID-Substrate core. We can open a design using open access, and then get a handle to our core, and then we can just ask our core to extract from the design to do the meshing and do all kinds of services. So at the end, we get a report with success or failure of the test. This is the abstraction of ID-Substrate core is done using Swing wrapper in the same way that is done using in open access actually. It's a standard way. So now let's see read use cases. And in these use cases, we see here this is a chip that was designed, and we see that there is no latch up in this chip occurring during simulation, but the chip explodes here. So we see on the right side the yellow circle, there is an explosion of the chip. So what we did actually is that we have extracted the substrate network and we hooked it into the particular circuit, or into this circuit. And then we find, when we did this, the latch up occurred in simulation. So you see 1 ampere in blue here on the supply current. We went further and we checked the corrective actions that was done by the designer to eliminate the latch up. So he added 3 different transistors here with different values. So when we add the transistors in the presence of the substrate network, the latch up disappears. So this means that we can do a prediction by simulation, and we can do also a prevention and verify by simulation. And this for sure helps in reducing highly the cost of design. This is another test case where we had a simple current mirror. We had the reference current here near the aggressor of Q1, and we had the reference current away from the aggressor of Q1. So we see after the extraction of the substrate network, in the case of without our substrate network, we see that there is nothing occurring and the current is constant, or is 0.173 millivolts, the voltage. But when we place the aggressor, IRF means the aggressor, we see that the current is, the output current has changed the sign actually. So the reference is positive and the output current is going negative. When we replace the reference current away from the aggressor, we see that the opposite occurs. We have the current, the output is positive and the IRF is positive. So these kind of things cannot be really predicted by the designer, because the designer is using typical design. In addition, that even when he simulates with SPICE will not detect this kind of phenomena without the substrate network. Also another example where we see that the choice of the wells, NWELL, can affect the I/O pad in different ways, and affect the output pad particularly. So we see here that without ID-Substrate, without AMS sub X, we get 0 voltage. But when we added AMS sub X, we get a negative drop on the well. And the negative drop is different from one well to the another. So each option gives a different value of the drop. So this is what we offer to founders today in order to use ID-Substrate. We get measurements from measurement data from tested structures. We generate the netlist for the CD substrate network for tested structure using ID-Substrate, and use this extracted netlist with measurement to calibrate the parasitic models. Once we have calibrated the models for the given technology, we can use it to analyze an industrial chip. So we take the layout of the chip, we generate the extracted substrate network for the chip, and we back annotate with calibrated models, parasitic models, and then we go to ADE, analog design environment, and simulate and see the effects appearing. So to conclude, we see that ID-Substrate was a direct commercial exploitation of photonics outcome. ID-Substrate also was used for systematic prediction and prevention of substrate noise coupling. So today we have an actual offer for foundries and IDM, and today also ID-Substrate is actually part of the AMS sub X PDK. And we seek more foundries today and IDMs to validate ID-Substrate on the technologies, and we as a sign-off procedure before tape-out actually.
Thank you. Great presentation. Any questions from the audience?
Yeah, hi, this is Paul at Google. I have a question. So I know from friends who work in the aerospace industry, building things that fly at high altitudes and in space, that latch-up is a huge problem due to radiation. Hit from cosmic rays. Can your tools help? And so today, they have these very laborious testing procedures they have to do on all analog designs in various, radiation sources, environments, and so they're flying all over the country and blasting their chips. could your tools really help with this process of verifying analog designs for space?
Yes, definitely, because if you refer to single event upset and multiple event upset, right?
Yeah.
Really? Yeah, definitely it can help because we provide you a physical model for the substrate.
Right.
You can excite it at any point you wish. So you can imagine having to inject different doses, different points of the substrate and simulate with spectral and to get the effect. Definitely this is something that you can do.
Sounds good.
Other questions?
This is Paul. I'm at Mythic. So I just have a kind of a low-level technical question, being a relative newbie to open access. On when you mentioned you use Swig in your own C++ core, and I'm just wondering if, yeah, you just mentioned it briefly there. I'm wondering if that the Swig wrapper was somewhat inspired by or modeled by the open access code itself, or whether you took a different approach.
No, the Swig we did the Swig wrapper for our C++ code, and to allow to interface all of our functions in Python, standard Python script.
Yeah, so I'm asking if you found a certain commonality between your approach and the approach in open access itself, or whether it's quite different.
No, it's almost the same. It's almost the same. Yeah.
Great, thank you.